All right, welcome to the deep dive. Today, we're going to be tackling something that's pretty fundamental to math.
Yeah.
It might seem simple at first, but it's actually like the basis for a lot of modern mathematics, the idea of sets. So just imagine, like, understanding the basic building blocks, right?
Yeah.
The things that let us construct, well, everything from the relationships between numbers to, shapes in geometry,
Right.
to even how we analyze probability.
Sets are really everywhere.
Yeah, they're kind of sneaky. Like, they just show up everywhere.
It's true. And, I think that's because they underpin huge parts of mathematical thought.
Yeah.
And the architect of set theory, as we know it, was a German mathematician named Georg Cantor.
Okay.
And he was active like late 19th, early 20th century. What's really interesting is that he wasn't actually trying to create this whole new field of math.
Really?
Yeah, his work on sets kind of came out of trying to solve problems with trigonometric series.
Oh, wow.
Which is a very specific and seemingly unrelated area of mathematics.
Totally different.
Yeah. It just goes to show you that really profound ideas can come from the most unexpected places.
Yeah, you never know where those breakthroughs are going to come from.
Oh, exactly.
That's so cool. And, it speaks to the power of really digging deep into problems. And the impact of Cantor's work is just undeniable.
Oh, yeah.
The mathematician G.H. Hardy, he famously said that set theory is the oldest and the youngest of mathematical studies. Like, old in the sense that the idea of just grouping things together is super intuitive.
Right.
We all do it.
It's natural.
But young in that, its formal development is relatively recent. And its influence is still growing today, which is pretty remarkable for something that starts with just basic collections.
It is. So in this deep dive, our aim is to give you a solid grasp of what sets are, the definition of a set, the key ways we represent them, and why this seemingly simple concept is so important. We'll be using our source material, obviously, as our guide. And we're going to try to illuminate these foundational ideas without, overwhelming you with too much complexity.
Right. We don't want to get lost in the weeds.
Exactly.
Keep it clear and simple.
Yeah. Our mission here is clarity and maybe a couple of those aha moments.
I love those aha moments.
I do.
All right. So let's start with the very core of it.
Right.
What is a set?
Right.
In our everyday lives, we're constantly dealing with collections of things, right? Like your collection of favorite books, or the group of friends you hang out with, or even the ingredients in a recipe.
Totally.
But math also has its own versions of these collections, right?
Right.
Like, think about the set of all even numbers.
Yeah.
Or the set of prime numbers.
Right.
Or even the set of points that make up a circle.
Right.
So we have this intuition about everyday collections, right? That's a good starting point. But for a mathematical collection to actually be considered a set, it needs to meet a really specific condition.
Okay.
It has to be well defined.
Okay.
And that's the really crucial distinction here. So a collection is considered well defined if, for any given object, we can definitively say yes or no to whether or not that object belongs to that collection.
It's in or it's out.
Yeah. There's no room for ambiguity.
No wishy-washiness.
Or personal opinion.
Yeah.
It's just like a clear-cut yes or no.
Right. Exactly.
And our source actually gives some really clear examples of this.
Okay.
So, like, the odd natural numbers less than 10.
Okay.
That's a set because we can very easily figure out which numbers fit that description. It's 1, 3, 5, 7, and 9.
Yeah.
No debate there.
Nope.
It's just like those numbers.
That's it.
Similarly, the rivers of India, that's also a set.
Yeah.
Because you can objectively figure out if a particular river flows through India or not.
Makes sense.
And the vowels in the English alphabet.
Okay.
A, E, I, O, U. Again, super clear, unambiguous collection.
Yeah, totally.
But let's look at something a little different.
Okay.
So let's say we have a collection like the 5 most interesting books ever written.
Okay.
Now, is that well defined?
I don't know.
Probably not, right?
Yeah, probably not.
Because most interesting, that's totally subjective.
Right.
Like, my top 5 might be completely different from yours.
Exactly.
And there's no objective way to settle that debate.
Like, whose opinion is more important?
Right, exactly.
Yeah.
So it's a collection of books, sure. But it's not a well-defined collection, and therefore not a mathematical set.
Right.
So the key is that you have to have clear, objective criteria for membership in the set.
Makes sense.
So to put it all together formally,
the
definition we're working with is that a set is a well-defined collection of objects.
I like it.
And within the language of sets, we use a few terms kind of interchangeably.
Okay.
So the objects that belong to a set, we can also call them its elements or its members.
Yeah.
You'll see all three of those terms used.
Okay.
And to make things a little more concise, math people, we love notation.
We do. We do.
So we typically use uppercase letters.
Okay.
Like A, B, S to represent sets.
All right.
And then the individual elements within those sets are usually denoted by lowercase letters.
Right.
Like A, B, S.
I'm with you.
And to indicate that an element A belongs to a set A, we use the Greek letter epsilon.
Okay.
So it looks like this. A.
All right.
And we read that as A is an element of A.
Okay.
Or A belongs to A.
Gotcha.
And then conversely, if an element, let's say B, does not belong to set A, we write BAA.
Right.
So if we take V as the set of vowels, that V would be true because A is a vowel.
Yeah.
And then BV would also be true.
Makes sense.
Because B is not a vowel.
Yep.
So we've got the definition down. We're starting to get a handle on the notation.
I think so.
But now the question is, how do we actually represent or describe these sets?
That's the big question.
And our source highlights two primary methods for doing this.
Okay, lamb on me.
Okay, so the first method is called the roster form.
Roster form.
Or sometimes the tabular form.
Okay.
And this one's pretty intuitive.
Right.
You just list out all the elements that belong to the set, separate them by commas, and then enclose that whole list within braces.
Those curly brackets.
Those curly brackets, exactly. So like, imagine you're writing your grocery list, right?
Oh, okay.
But instead of just putting it in a straight line, you put those curly brackets around it.
Got it.
So, for example, if we want to represent the set of even positive integers that are less than 7, in roster form, we would write 2, 4, 6.
It's simple and
super simple and direct.
Yeah.
Just like a grocery list with curly brackets.
That's like.
And there are a couple of important conventions to remember when you're using roster form.
All right.
So first, the order in which you list those elements doesn't actually matter.
Okay.
So the set 1, 2, 3 is exactly the same as the set 3, 1, 2.
Okay.
Same elements, same set.
Got it.
And also, you only list each distinct element once.
Right.
So if you're looking at the set of letters in the word Mississippi, the roster form would be M-I-S-P.
Oh, interesting.
Yeah, you don't have to list out all the repeated letters.
You just need each one once.
Yeah, we're interested in the unique members of the collection.
Yeah, mix and...
No need for duplicates.
So what's the other way to represent a set?
The second method is called the set builder form.
Set builder.
And so instead of explicitly listing every single element, you basically describe the elements by stating a common property or a rule that all the elements in that set satisfy.
Okay.
And that no element outside the set possesses. So the general notation for this is X has a certain property.
Right.
And that colon in the middle, that's super important.
What does that mean?
That's read as such that.
Okay.
So it's like, instead of saying, here are all the members, you're saying, here's the condition that determines the members.
Okay.
And our source uses the vowels again as an example.
Okay.
So in set builder form, the set V of vowels can be written as X. X is a vowel in the English alphabet.
Okay.
So it reads, the set of all X, such that X is a vowel in the English alphabet.
Gotcha.
And the set builder form is really flexible.
Okay.
So for instance, if we wanted to represent the set A of all natural numbers between 3 and 10, we could write that as X. X is a natural number and 3 is less than X, which is less than 10.
Okay.
So that very clearly defines the type of numbers we're talking about and the specific range that they fall within.
All right.
So if we look back at some of our earlier roster form examples,
Yep.
we can see how they might look in set builder form.
Okay.
So the set of all natural numbers that divide 42,
Right.
which in roster form was 1, 2, 3, 6, 7, 14, 21, 42,
Right.
could be written in set builder form as X. X is a natural number which divides 42.
Okay.
Much more concise.
Yeah.
And then the infinite set of odd natural numbers, 1, 3, 5, and so on,
Right.
could be represented as Y. Y is an odd natural number.
Yeah.
So it's almost like
It's like a club, and you're defining it by the rules to get in.
Exactly.
Rather than just listing out all the members.
It's a much more elegant way of doing it.
I like it.
And it's really powerful.
Yeah.
Especially when you're dealing with sets that have a huge number of elements or even infinite sets, right?
Right.
Because listing every single element in roster form would just be impossible.
You'd be writing forever.
Right, exactly.
So our source provides some examples where we get to see these two forms in action.
Okay.
And we can practice converting between them.
Let's do it. So example 1
Okay.
asks us to write the solution set of the equation x squared plus x minus 2 equals 0 in roster form.
Okay, so the first step here is we actually have to solve the quadratic equation.
Right.
So if we factor x squared plus x minus 2, we get x minus 1, x plus 2 equals 0.
Right.
And that gives us two possible solutions for x.
Okay.
So either x minus 1 equals 0, which means x equals 1, or x plus 2 equals 0, which means f equals negative 2.
Gotcha.
So the solution set in roster form would be 1, negative 2.
Nice. Easy PD.
Yeah, not too bad.
All right, so example 2 asks us to take a set that's given in set builder form.
Okay.
So it's x is a positive integer, and x squared is less than 40.
Okay.
And write that in roster form.
All right, so basically we need to find all the positive whole numbers that when you square them, you get a number less than 40. So let's try it out. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36.
Let's go.
Keeping going. Okay, now if we go to 7, 7 squared is 49.
Too big.
Which is greater than 40. So we have to stop at 6.
So it's all the numbers up to 6.
Exactly. So the set in roster form would be 1, 2, 3, 4, 5, 6.
Perfect. Example 3 gives us a set in roster form.
Okay.
A equals 1, 4, 9, 16, 25, ...
Ooh, ...
Yeah, I think those ellipses at the end are giving us a hint.
Yeah, I mean, keep going.
Yeah, that this is an infinite set.
Right.
So we need to write this in set builder form.
Okay, so the key here is to recognize the pattern, right?
Yeah, what's the connection?
Like, what do all these numbers have in common?
1, 4, 9, 16, 25.
They are all perfect squares. The natural numbers.
So 1 is 1 squared, 4 is 2 squared, 9 is 3 squared.
Exactly, and so on.
Okay.
So we can actually express this in set builder form in a couple of ways.
Okay.
One way is a equals x is the square of a natural number. Or we could be a little more precise and use mathematical notation.
Okay, I like being precise.
Me too. So we could write it as a equals x equals n squared, where n is an element of n.
Okay, break that down for me.
So that n is an element of n, that just means that n belongs to the set of natural numbers, which is 1, 2, 3, and so on.
Gotcha.
So we're just saying that x is the square of any natural number. So that's a little more formal.
Yeah, that formal notation really, nails it down.
It does.
Okay, example 4.
All right.
Gives us the set 1/2, 2/3, 3/4, 4/5, 5/6, 6/7.
Oh, okay.
And asks for the set builder form.
All right. This one's a little trickier, I think.
Yeah, it looks more intricate.
But careful observation is key here.
What are we looking for?
We need to find the relationship between the numerator and the denominator in each of those fractions.
Okay.
So notice, in every case, the numerator is 1 less than the denominator.
Oh, yeah, you're right.
And the numerators themselves, they go from 1 up to 6.
Right?
Right.
So we can actually capture this pattern in set builder form like this. X equals n over n plus 1, where n is a natural number and 1 is less than or equal to n, which is less than or equal to 6.
Wow. Okay.
So that basically covers both the rule for generating the elements and the specific range of values for n.
Yeah, that's like finding the underlying formula that produces all the elements in the set.
It is.
I like it.
All right, so example 5 is a matching exercise.
Ooh, fun.
Which should help us, test if we really understand this.
Yeah, solidify the concepts.
Exactly.
So we've got a list of sets in roster form.
And another list in
set builder form, and we have to match them up correctly.
Let's do it.
Okay, so let's take them one by one.
Sounds good.
So the first roster set is PRINCIPAL.
Okay, so that looks like it matches up with choice, D, which reads, X is a letter of the word principal.
Yeah, perfect match.
Because remember, in a set, the order of the elements doesn't matter.
Doesn't matter at all.
And we only include each unique element once.
Exactly.
Okay, next up, we have the roster set 0.
Okay.
So which of the set builder descriptions fits this one?
So option C says XX is an integer, and x plus 1 equals 1.
Mm-hmm.
And if you solve that equation,
Yeah.
you find that x must equal 0.
Right.
So that's got to be the one.
That's our match.
All right, moving on.
Right.
The roster set is 1, 2, 3, 6, 9, 18.
Okay.
Now, looking at the remaining set builder options, option A says x is a positive integer and is a divisor of 18.
Mm-hmm.
So if we list out all the positive integers that divide evenly into 18, we get 1, 2, 3, 6, 9, 18.
Perfect.
So that's got to be it.
All right, and that leaves us with roster set 3, -3.
Okay.
And the only remaining set builder option is B.
Which is
X is an integer and x.
We get x squared equals 9,
Yeah.
which means x can either be 3 or -3.
Perfect fit.
I like it.
So that matching exercise is really helpful.
Yeah, it's good practice.
Yeah, for understanding the relationship
Mm-hmm.
between those two ways of representing sets.
All right, so we've done a good deep dive today
Yeah, I guess so.
into the fundamental concept of a set.
Mm-hmm.
We've understood it as a well-defined collection of objects.
It all comes back to that well-defined
Yeah.
criteria.
And we've explored the two primary ways to represent these sets.
Roster form.
Raw matter form, where we list out the elements,
And set builder form.
and set builder form, where we define the elements by some shared characteristic.
Right.
And this is powerful stuff.
Oh, yeah.
Because from this, seemingly simple idea of just grouping things together in a well-defined way,
Mm-hmm.
we can actually build up this whole universe of much more complex math concepts.
We can.
It's crazy. It's like the basic.
Yeah, it's the bedrock for understanding relationships
Mm-hmm.
between mathematical objects, functions, so much more.
It all comes back to sets.
It really does.
Yeah.
So our final thought for you.
Okay.
Consider how this basic idea
Yeah.
of a well-defined collection
Mm-hmm.
allows us to construct these incredibly intricate
Yeah.
and useful mathematical systems.
It's pretty amazing.
It makes you wonder about, other seemingly simple concepts, but in different fields, right?
Yeah, could they also have similarly profound and far-reaching implications if we just define them with the same precision?
Exactly.
Mm.
It really underscores how important clear definitions are
Oh, yeah.
as the starting point for any area of knowledge.
Absolutely.
So if this intro to the world of sets
Mm-hmm.
has, piqued your interest,
Yeah.
there's so many cool avenues to explore further.
Oh, tons.
You might want to look into the concepts of subsets
Okay.
or the various operations you can perform on sets, like union and intersection, or even the visual representations of sets using Venn diagram.
Ooh, Venn diagrams. Those are cool.
I love Venn diagrams.
Yeah, they're great.
And these all build directly upon the ideas we've talked about today.
Exactly.
So they're great next steps if you want to keep learning about sets,
Totally.
because grasping these basics really unlocks a powerful way of thinking about and organizing information,
Mm-hmm.
not just in math, but really in tons of different areas of life.
Yeah, absolutely.
Well, thanks for taking this deep dive with us.
Thanks for having me.
It's been fun.
It has been fun.
All right, until next time.